Our next presenter is an associate professor of podiatric medicine and neuroscience at the Rosalind Franklin School of Medicine and Science. He works in the Center for Lower Extremity Ambulatory Research as director of the Human Performance Laboratory. Dr. Flanagan's background includes training in brain stimulation, imaging, neuroendocrinology, and stress physiology. His overall research interests emphasize neurobiological aspects of human health, performance, and disease. Dr. Flanagan's laboratory uses varying scientific techniques to better understand and improve brain-body interactions in humans in vivo. Ladies and gentlemen, please welcome Dr. Shawn Flanagan.
Thank you so much. Is this working? Can everyone hear me?
Yeah.
Okay. Wonderful.
I think so.
All right. Well, first and foremost, thank you, Megan. Thank you, organizers. Thank you, Candace, for helping get all of this going. Thank you to the attendees for sharing your work and your stories. They have been inspiring, and I'm honored to be here. So my goal today is twofold. I am excited to share with you the results of some of our recent work, which I believe has profound implications for whole force optimization. And importantly, I believe that this work represents a model for effective collaboration between academia and field specialists, translational environments, right, to get the high quality basic scientific work that we do into the field for the benefit of the operators, right, and that ultimately is the goal. And I think that what we did, which was hard work, could serve as a model for others, and it's work that we need to continue. So, first and foremost, the Army study. This was an effort spearheaded, the brainchild really, of Julie Hughes, Susan Proctor, Carl Friedel, Stephen Fallis, and many others over a long period of time. And so the goal of this effort was to collect longitudinal data from 5,000 recruits, men and women in basic Army combat training, and to survey them for 2 years, their medical records 2 years after that, to better understand the determinants of performance and injury. What goes well, what doesn't go well, what might explain it. Everything from contraceptive use to vitamin D status to tobacco use to genetic factors to environmental and behavioral factors, right? Who's successful at the end of basic Army combat training and why? And what can we do to improve training doctrine? What can we do to improve health? So this is a Herculean effort that took years. And it involved a ton of collaborations. And Chris Conaboy and I were fortunate enough to be included as collaborators and to take a small slice of the study to help advance a specific question. And in this case, that specific question relates to bone. And I'm talking about adaptive changes in bone formation, right? Bone is an incredibly adaptive tissue. It was once thought of as this static, hard structure, doesn't really change. We know that that's not true, right? It can increase in its density, it can decrease in its density, its properties become stronger, become weaker. It's responsive to what we do and what we don't do and how we do it. And as many of you know, as well or better than anyone, bone stress injuries and bone fractures are endemic in the military. And women bear a burden of stress fracture at a rate of about 3 to 4 times what men experience. And these bone stress injuries are really a national security threat. They are endemic. They compromise our readiness, our lethality. They result in massive amounts of lost duty time, morbidity. And so basically they are an enormous they represent an enormous human and economic cost and burden. And so what we need are better, non-invasive, unobtrusive predictors of bone stress injuries, right? Biomarkers that can tell us how people are responding to the stresses that they experience every day in their military service, and will perhaps give us, so to speak, a fork in the road, right? A means to say, hey, we need to intervene. We need to take a different path. We need to back off. We need to prioritize recovery. We need to prioritize vitamin D status. We need to take another look so that we can avoid this injury before it occurs. Because once it occurs, there isn't much that we can do. And the prognosis isn't that good. So the best strategy is to avoid it in the first place. And that's what I'm talking about today. Now, we didn't do work with bone stress injuries. We started with a more conservative question, and that's the ability to detect and distinguish adaptive changes in bone formation, right? And so if you look up in the upper right quadrant of this huge slide, it's obnoxious, and I did that tongue-in-cheek. We're not going to get into the weeds, okay? We'll get to the point on that in a moment, right? But hopefully, just stay with me. I think it's a decent point, okay? So let's talk about a few things. First is urine. Now, do I specialize in urine? Is my background in urine? I mean, no, I do neuroendocrinology, really. I usually take blood. I'm not all of that interested in urine, but here's the thing. No matter how much I would rather get plasma or cerebral spinal fluid or some other thing that I think is closer to the structures that I'm really interested in, there are people who are not going to be willing or able to give it. And there are environments where it will be very difficult to collect and preserve and process in a manner that will yield useful results. With urine, you're doing it every day, whether you're in a study or not. Abundance is never an issue. We'll always be able to get enough, right? It's been at body temperature in your bladder for some time. The proteins that we're going to degrade have largely degraded. What remains is more stable. And so what I'm trying to say is, in this case, we could take the basic scientific proclivities, we could put them aside, and we could say this is a really good compromise. Because if we can find something in this substrate, we could develop assays that are fieldable. I'm talking about peeing on a stick and getting a result that we can use to change programming, to change what the soldier does, right? Harder with blood draws, even harder with other tissues. Saliva can be good. Saliva has a number of problems as well. It's tougher than urine, I'll say that. Okay, so urine is not just junk. It's not just trash. I wasn't really sure about its constituents until we got into it, right? But it turns out that about 30% of the protein contents in urine comes from circulation, not just junk proteins, garbage proteins, kidney proteins. You can pick up proteins specific to the immune system. You can pick up proteins that come from the brain. You can pick up proteins that come from every single organ in the body in urine. It's truly an integrative, systemic medium, right? Now the question is, can we detect things that are useful in that medium? And that's a different question sometimes. And if we couple it, as you can see, upper left quadrant, with some of the newer, more sensitive bone imaging technologies, maybe we can get some insights about what's going on in bone in terms of bone physiology, musculoskeletal health, and the response to, in this case, basic Army combat training. And that new technology was high-resolution, peripheral computed tomography. It's word salad, but it's a fancy way of saying that we can image human bone, like in live, living, breathing humans, at a resolution on the order of microns. That's 1/1000th to 1/100th of a millimeter, right? And with that kind of resolution, we can detect changes in bone that you otherwise wouldn't be able to detect with any other technology until the changes have accrued for many months, maybe even years. But here, we're talking about the ability to detect changes that occur over the course of weeks. Why does that matter? Because basic Army combat training is about 10 weeks long. So that brings us to the work. We collected urine samples, mostly from women, because bone stress injuries are more problematic, and we are problem-focused. We work to solve problems. And so we collected urine samples in basic Army combat recruits at the beginning and at the end of basic Army combat training. And we also collected images of their tibial trabecular bone volume fractions. You can see an example of a reconstruction that we would get with the high-resolution peripheral computed tomography scan. We took those urine samples and we analyzed them with state-of-the-science, basic science, laboratory techniques. What was it? I don't know if anyone here cares. We could get into the weeds, right? It's an ultra-high performance tandem quadrupole orbitrap tandem mass spectrometry system. Tandem, yes, yes. Okay, good. All right, we're good. All right, cool. I'm done. So here's the thing, all right? It's a $1 million piece of equipment that's been further customized, and the point is, if there's a protein that's reliably detectable, it's capable of detecting it, right? And it's not going to make its way into clinics. It's not going to make its way into Fort Jackson, not in our lifetimes, okay? But it's the type of technology that we can maintain and optimize in an academic environment. But that's not the goal. Our goal is to take what we learn in that ivory tower and translate it to the benefit of the warfighter here and now. So let's go there. All right, we collect these urine samples, and what we do is we figure out how to collect them, how to process them, how to preserve them, whether or not freeze-thaw cycles matter, if we should normalize the pH, if we should normalize the protein concentrations, if we should remove plastic contaminants. There's a lot of that in our pee, unfortunately, PEGs. I know everyone's probably thrilled to hear that. I can confirm that that is not controversial. If we analyze your urine, we will find plastics in it, okay? Bacteria, fungus, all other kinds of human things, right? And so all of that work, oh, and I should say protein enrichment, that's a big one too. All of that work to get to the point where we have a high quality procedure that consistently works, right? It's reliable, it's sensitive, it's specific, it works. So, okay, that's all I have to say about all of that stuff. All right, and the point is, let's take a look at the men and women who we studied. All right, what we see here is their trabecular bone volume fractions, right? At the beginning of basic Army combat training, there are no differences, no discernible differences between the men and the women who experience the biggest improvements and smallest or even negative improvements in bone adaptation. We deliberately selected that. That was something that we were able to do because of the structure of the study. So same physical activity patterns, same body composition, same nicotine use, contraceptive use patterns. You know, as far as we can tell, these people are identical. And yet, we can divide them into two groups, and half of that group experienced enormous improvements in bone adaptation, in bone formation, which is a good thing, right? That's what we're hoping for. The other half experienced no improvements at all, right? And then the question is, how do their urinary proteomes differ? Do they differ? And are those differences useful? And what can they tell us? And the answer is, they do. And let's zoom back. So, results. Everybody wants to know the results. So you did all of this stuff with this fancy technology. What did you find? Well, what we found was that we can detect well over 10,000 peptides associated with well over 1,300 proteins. And those proteins are reflective of hundreds of biological processes. It's a treasure trove. We can get a ton of information from the urinary proteome. And we can get that information from samples that were not collected in our laboratories, samples that were collected at Fort Jackson, Fort Sill, anywhere in the world, okay? We can get that quality of data. High-end, state-of-the-science data. These are just examples of the biological processes that we can detect. We can see that from the beginning to the end of basic Army combat training, the proteome changes, which isn't surprising. It's stressful, it's an enormous change in lifestyle, it's an enormous change in behavior. It's designed to be stressful, right? It's designed to be tough. So most of what we see are increases in markers of innate immunity. Now, I wasn't necessarily expecting that to be the dominant biological process that we detected in response to basic Army combat training. I thought it might be a series of biomarkers specific to like collagen turnover, tendon health, muscle health, other structural things that are being stressed, but it's the immune system. And that makes sense. The innate immune system plays a fundamentally critical role in wound healing and in inflammation and in tissue adaptation. So it's there, it's always been there. And with this technique, it really shines. What we also saw, were a ton of biological processes that are relevant to many of the questions that have been brought up and the topics and the problem spaces that have been discussed during the symposium, right? We see changes in proteins responsive to estrogen physiology, axonal injury, excretion, which we would expect. This is the urinary system, after all. pH responses, tissue remodeling, muscle cell proliferation, bone development, nutrient level responses. Maybe this is useful for assessing responses to nutritional interventions. Collagen metabolic processes, sure, why not? Tendons are stressed, bones are stressed. This is a stressful process. And I could go on, but skin development, even toxic substance responses. It's really interesting. And we've only scratched the surface. But the big thing is that individuals who displayed, the hand-selected individuals who displayed the biggest improvements in adaptive bone formation, when we compare them to the individuals who experienced the smallest or nil, negative even, improvements in adaptive bone formation, there are two adaptive immune-related biomarkers that really differentiate them. One is an immunoglobulin. The other one is a spike protein. And what's interesting here is that these are insights that we would not get from the other proxy measures that we typically use, right? If you take current, kind of high-end imaging technologies like DEXA scans, right? You can get body composition, you can get bone mineral density, you can get lean mass, fat mass, you can get a bunch of useful measurements, right? With those, none of those measures correlate with the differences in adaptive bone formation that we detected with the high-resolution peripheral computed tomography. They don't, right? We cannot tell what's going to happen in terms of adaptive bone formation, who's going to respond well to training and who won't, based on changes in muscle mass or fat mass. You would hope that would be great. That wasn't how it turned out working in this case, right? But these two biomarkers, as you can see in the bottom right panel, were strongly related, right, to the differences in adaptive bone formation. So this is work that we need to replicate in an independent cohort. It's work that we need to fund and expand upon. And if we can do that, we have a shot at being able to miniaturize it and make it fieldable, right? This isn't about the fancy technologies I've discussed today. It's about what we find with those technologies. And what we find is something that we can translate to fieldable assays, fieldable kits, because those entities exist. We have those relationships. So the first thing we need to do is make sure that it's real, right? And make sure that it consistently works. And once we do that, we can build something that someone can take out of a package, use, and then get really good diagnostic prognostic information to prevent these injuries. And obviously, we need to better understand what's going on with bone stress injuries specifically, and not just adaptive or maladaptive changes in bone formation. So yeah, that's my presentation. I'm happy to take questions at any point. And I would say just two unrelated notes, I guess on two personal notes. The first is that as I was thinking about Sydney's presentation just a moment ago, a couple of things came to mind. One of those things is that, you know, I can say, I hear you and I see you and others hear you and others see you, and it isn't thousands, it's many, many more than that. That's the first thing. And the second thing is that, on a personal note, I think meritocracy is a nice idea. The problem with it in the real world is that it isn't that it begins, but that it often ends with me. And that's all I have. Thank you.